In this video, we are going to look at a nuclear exam question. So pause the video now and try part A. So ask for the definition of decay constant. So as usual in physics, it makes sense to refer to a formula if possible. And the standard formula for decay constant is this. So activity divided by the total number of nuclei is decay constant. So in words, we can say that the decay constant is the number of decays per second divided by the total number of nuclei. Now, a slightly better, or maybe not better, but a definition that maybe makes more sense to you if you're talking about probability and used to probability is the decay constant equals the proportion of nuclei decaying in a given time, because then that obviously links nicely to the probability of decay, which is what we often talk about. What are the differences between X and Y? Well, in the question, it tells you the decay constant of source X is greater than that of Y. So if this is going to increase, then what's going to happen? Obviously, this must increase as well. So for X, the activity of X will always be greater. Or what follows from this, the number of nuclei in X will decrease far faster than in Y. Either of those is fine. Part B, pause the video now and try this question. So this graph is an activity against time graph. Now you're probably used to seeing this kind of shape here, the classic exponential decay, which follows this mathematical formula. However, here they've given us a log graph, and you can tell it's a log graph because the size of these bars are decreasing each time. So that's a big clue, it's a log graph. On the x-axis, it's not a log graph because these are all equal each time. So we need to solve this equation. So what is our initial activity? 10 to the 5. Sorry, our initial activity is A0, that's 10 to the 5. What is our activity at a given time? Well, I'm going to pick this point down here, or you could pick any point on the line. So I'm going to say that this activity here is 10 to the 2. And what time does that correspond to? That corresponds to a time of 6.9 times 10 to the 6 seconds. So now we're solving this equation here. So if you're not sure how to do this, one way of doing it is this. I'm just going to leave it as t for now, just to save me writing that long number. Now I can log both sides. And if we log an exponential, then we obviously just end up with this. And then it's trivial now to solve this equation. You just plug this into your calculator. When you do, you'll see that it rounds to this number. So I've obviously made a very silly mistake. That should be times 10 to the 6. Okay, final two parts of this question. Pause the video now and try these questions. So part I, calculate the half-life. So importantly, we've been given the activity from the previous question, 1.1 times 10 to the minus 6 per second. So we need to recall that the relationship between half-life and activity is this. Is this. Let me just tidy this up. So now if we plug in our activity, we obviously know what ln of 2 is. we get our half-life as 6.9 times 10 to the 5 seconds. And then in a unit that's more useful, could be days, could be weeks, could be months, could be years. Here it works out to days. So obviously that is just a little bit of trial and error, dividing it until you get the time. Actually, no, so it tells us, doesn't it, in days? So we've been told what to do. Calculate the initial number of atoms in a sample. So you might immediately think of this, which was what my first thought is. But this is not helpful because we actually don't know what this is. So we need to go back to the relationship from the previous slide and say that activity is minus the decay constant times by the total number of nuclei. And obviously remembering that activity is the change in the number of nuclei over the change in a given time. So now the number of nuclei is the activity divided by the decay constant. And if we want the initial number, then we need the initial activity. So what's the initial activity? Well, it was 10 to the 5. So the initial activity was 10 to the 5, and our decay constant is 1 times 10 to the minus 6, which gives our starting number of nuclei as 1 times 10 to the 11. Sorry about that. 1 times 10 to the 11 atoms is the answer.